We present XPG-RL, a reinforcement learning framework designed to improve efficiency and robustness in mechanical search tasks through interpretable, priority-guided action selection. To understand the problem setting, let's first define what mechanical search entails. Mechanical search refers to the task of retrieving a specific object from a cluttered environment using a robotic manipulator. As humans, we naturally execute a sequence of intelligent actions, like removing occlusions or changing our viewpoint, to uncover and retrieve the target. These tasks are common in real-world scenarios such as warehouse logistics or home organization, but they remain challenging for robots due to visual clutter, uncertainty, and sparse rewards. Existing methods often perform redundant actions or fail to complete the task efficiently. This brings us to our central question: can we enable similar capabilities for robotic manipulators? In this approach, we aim to integrate domain knowledge with learning-based policies to guide efficient decision-making in complex, cluttered environments. The proposed XPG-RL consists of two core components, a perception module and an RL-based decision-making module. The perception module processes RGB-D inputs to produce an object-level depth map and a semantic mask for the specified target, using segment anything model for segmentation and pose CNN for recognition. This compact scene representation is then passed to the decision-making module, which formulates the task as a partially observable Markov decision process. The agent predicts adaptive thresholds and selects among a set of priority-guided actions, including grasping the target, removing occluding objects, or adjusting the viewpoint. Let's take a closer look at how these thresholds guide action selection within the XPG-RL policy. XPG-RL uses a structured action hierarchy guided by Q values and adaptive thresholds. A Q value represents the success likelihood of executing a specific action given the current observation. In our system, the Q values for grasping the target and removing occluding objects are computed using any grasp. At the highest priority level, if the Q value for grasping the target exceeds a threshold tau1, the agent directly attempts the grasp, completing the task. If the target grasp Q value is below tau1, but the occlusion removal Q value exceeds a second threshold tau2, the agent removes the occluding object and updates its observation. If neither Q value exceeds its respective threshold, the agent adjusts its viewpoint to improve scene understanding. This fallback behavior helps reduce risk under uncertainty. This interpretable switching strategy allows the agent to act efficiently and robustly in cluttered environments. We now demonstrate how XPG-RL behaves in a real-world task using these three action modes. In this real-world example, the robot is tasked with retrieving the banana from a cluttered scene. The Q value for grasping the target is low, falling below the learned threshold tau1, which indicates that a grasp would be uncertain or unsafe. However, the Q value for removing an occluding object is high, exceeding threshold tau2. As a result, the agent selects the remove occlusion action. This enables the robot to clear a blocking object and improve the visibility of the target before making a grasp attempt. After the initial occlusion is cleared, the robot evaluates the scene again. Now, both the target grasp Q value and occlusion Q value remain below their respective thresholds. In this case, the agent chooses to adjust its viewpoint, repositioning the camera to gather better visual information about the target. This decision reflects XPG-RL's ability to defer physical interaction when uncertainty remains high, ensuring safer and more informed actions. With the improved viewpoint, the Q value for grasping the target now exceeds threshold tau1. Confident in its estimation, the agent proceeds to grasp the target, successfully completing the task. This sequence illustrates how XPG-RL combines perception, priority-guided reasoning, and learned thresholds to act efficiently in cluttered real-world environments.